Hi there, this is Dr. John, your physics and math professor, and we've been looking at various different circular motion problems. For example, here's one that we do about a car going around a curve. Here's the car moving this way, it goes around this curve, and we say that the road has a curvature, a radius of curvature, as if you put a string here and draw it. That's like your curvature. I've tried to sort of duplicate this over here. It's got this curve, the radius of curvature. And then we talk about the fact that the car is going to feel an outward centrifugal force as if an artificial gravity is trying to push it off into the bushes, which is going to be mv squared over r, or it's going to feel an acceleration that way. And we're going to have to create an acceleration inward using the tires or the bank of the road to keep us on the road as we go around this curve, equal to v squared over r, or mv squared over r. That's called the centripetal or centripetal acceleration or force that we're going to need to create to compensate for the sense that we're being pushed off into the bushes, which is really just the idea that the car wants to keep on going in this direction, but we want to pull it in this direction, so its inertia is going to push it off into the bushes over there. Now, we've used this a number of different times, v squared over r. We use this in various different ways. For example, here, of course, we used it with a car going around a curve. We used it with a stone being whirred, like a shepherd maybe using a stone in a slingshot and then slinging it off. We use that because it's whirring around as well. We use this for a Ferris wheel where they're going around the Ferris wheel like this. Various different applications of this thing, and we just used this formula. We just popped it out. We didn't explain where we got it from, and today I'm going to try to develop that for you. Hopefully you can understand where it comes from. This is probably not something you're going to have on a test, but it might be something that's curious and useful for you to have. So I sort of duplicated what we have here. This could be any circle. This could be the rock whirring around. This could be the part of the Ferris wheel here, top of the Ferris wheel going down to the bottom. We're going to try to see how we can create this acceleration, and of course the force, just multiply the mass of the object to get the force that is needed to create this acceleration. So let's start off by having this car, or whatever it is, be going in this direction. I'm going to call that V1. And then after a while, it's going to be going in this direction, V2. Now these two are both vectors. V1 and V2 are vectors. This one has a upward direction, this one has this direction, and in the illustrations we're using, our velocity is always the same. The magnitude of velocity, the absolute value of the vector is the same, but the direction of the vector changes. And we say that there's an acceleration acting in the inward direction. And this is how we illustrated it for various uses. Let's say you're starting to go like this with a car, but you want to be turning this way. So you're going to have a little bit of an acceleration that way, which is going to then be moving you this way. See, we're turning the top of the vector. Then we have a little bit more in this direction now, because we want to go this way. And a little bit more this way to go this way and end up going straight this way. So notice in each case, our acceleration is toward the center, but we've never figured out what the magnitude of that is. So we're going to take these two extreme examples, starting off here and going to here. So this is like a 45-degree change. We're going to do this with the instantaneous. If you're into calculus, if you've done that already, we're going to do this instantaneously just right here. But I'm going to show you this 45-degree calculation first of all. So here's our two vectors drawn over here. Here's this first vector and then the second vector. So this is V1. This is V2. Now how do we figure out what vector we need to add to this to get this one? Well, it's going to be V1, remember each of these is vectors. I just haven't drawn the vectors on top of each of them. V1 plus some unknown vector, delta V, a change of velocity. What velocity do we need to change is going to be equal to V2. So this original velocity plus the unknown change of velocity is going to be equal to this. Now if we sketch this out really nicely here, we'll want to have this here. We want to separate this here. So how do we do that? We put delta V. Delta is often used, it's a Greek letter D that we often use for change. And that's going to be equal to V2 minus V1. These are vectors, of course, remember. And the way that we like to do vectors, we don't like to put a minus sign in vectors. We'll tend to say V2 plus the negative of V1. These are vectors again. That's what delta V is, another vector. So this here is what we want to sketch out. Let's sketch this out. V2 is this way. Where do I draw this? Let me draw this maybe right here between the two. Here's V2, straight that way. And then V1 is upward, but we'll want to add that to the negative of V1, which is going to be like this. This is negative v1, the vector, of course. I've just flipped around the direction, kept the magnitude the same. And then this is this plus this. So if we want to take this plus this, we'll go from the tail to the tip. This is going to be delta v right there. I'll erase a couple of things here. What if we put the change here, the delta v, between these two? Of course, I'm leading you toward doing this with an instantaneous thing right over here. But if we put that between the two, it would seem to make sense. In that case, the delta v seems to point right toward the center of curvature here, which is what we generally have for centripetal acceleration or the centripetal force. Now, what is the magnitude of this here? Well, if you notice here, this is a right angle because we're doing this at 45 degrees. And the length of this delta v, the length, the absolute value, delta v here, just the length, is going to be equal to this times the root of 2, because it's a right angle 45-degree triangle. So it's going to be root of 2 times the length of v1. We're just concerned about the length. The lengths of both of these are the same. So this is how we can calculate this here. So that's the change in velocity. How much time occurs during this quarter of a circle? Well, because we want to have the change in time. So if you remember, velocity is equal to the distance you go divided by the time. If we want to solve for time, we'll move time over here and velocity down here. So I'll put time here and velocity here, like that. So what distance do we go here? This distance. That distance would be this arc length. If you remember from your geometry, the arc length of a circle, an arc is just a portion of a circle. The arc is equal to the angle, this angle in radians, times the radius, times whatever the radius is here or the radius is here. So the angle times the radius. And the angle here, because it's a quarter of a circle, is pi over 2. So that's equal to pi over 2 times the radius. That would be the distance it goes. And what's the value of the velocity? Just the absolute value. Well, that would just be v, either v1 or v2. We don't need to use v1 or v2. They're both the same. So the absolute value of v1 is just going to be equal to v. So this would be this value over here, which would be the time. So if we want the acceleration, it's going to be the change in velocity divided by the change in time. So it's going to be this, root 2 times v divided by pi over 2 r over v. That's all of this. This v now can go over here. We have v squared, like that. I'll just erase this. And this 2 can go up here, just to move it up there. And then we're going to have this. We're going to have 2 root of 2 over pi v squared over r is the acceleration. Now that's not quite this, v squared over r. That's v squared over r times this. And if you happen to calculate this, this here is actually equal to about 0.9. It's not quite 1. If this was 1, then this would be v squared over r. Now, of course, we've sort of used 90 degrees as our change, so it's not really a very accurate instantaneous calculation. So I'm going to erase this, erase some of this, and redo my calculation here using instantaneous. And just keeping this in mind, how we did this with 90 degrees, you could do this then with 45 degrees, you could do this with 30 degrees, and you're going to find this number keeps getting lower and lower. I mean, this number here keeps getting closer and closer to 1 as you get closer to using just 0 degrees here. Of course, you can't use 0 degrees. Let's just erase a few things and I'll start over again. All right, I'm back. I've resketched this diagram here. Here's the initial velocity, v1. Remember, v1, v2 are vectors. They have direction and magnitude. The magnitude is the same. So the absolute value of v1 is equal to the absolute value of v2. We'll just call that v. It's going to be the same as this v over here. So here we have v1, and then v2 is in a different direction because of this angle. I'm going to take this angle, of course, and shrink it later to be very close to 0, like in a similar way as you would do with calculus. And this arc length is theta times r, and here's the radius. I've drawn those all in there. From our sketch before, you'll recognize this. So what I've done here is I've said v1, this one here, plus the delta v, the change in velocity, which is a vector, is going to be equal to v2. That's sort of self-obvious. Now we take this v1 to the other side and we make it a minus v1, but we don't like to do that. We like to add a negative v1, because then we just reverse the direction. So here we want to draw delta v. So notice here delta v is equal to v2. Notice I took v2 as an angle here, like this. And then minus v1. v1 is straight up, so I just flipped it, and I put it right here. Tip to tail, and then straight down. So delta v then would be from this tail to this tip, just like this. Now, you might think, well, so what does that help us? Well, if we know this angle here in between, this angle, if you can think of as this angle goes down, what will happen to the angle between these two, v1 and v2? The angle between v1 and v2 will also shrink. So this angle over here, I could prove that with some more geometry, but I figured you can sort of see that. If you shrink this angle will be the same as this angle up here. The angle between these two is the same as this one. Oh, that's all that you need to know, and then we can do the rest of the solving. What is delta v? Well, if you happen to recognize this, this is a triangle. It's not a right angle triangle anymore, because you don't know exactly what these angles are. But this is a triangle where you know the angle between them and you know the length of the two sides. The length of the two sides here, both of them are just v, because they are identical in magnitude. So the magnitude of this is the same as the magnitude of this, the lengths. We just want to know the length of this. The direction, it looks like it's basically toward the center here. Geometry sort of looks like it's straight toward the center. As these things collapse right upon each other, this would be straight toward the center right here. If you can see that, that's the only proof I'm going to do of that one for now. I just want to find the length of this. So to find the length of this, if you remember your cosine law was this, that the length of this one here, so if you had a triangle like this, A, B, C, and then you knew the angle C there. Remember the length of side C, C squared is going to be equal to A squared plus B squared. That would be if this was a 90 degree, minus 2AB cosine theta. This is the cosine law. That's that cosine, that's the angle C right there. So I'm going to rewrite that for this. So delta V here squared is equal to V1 squared plus V2 squared minus 2 V1 V2 cosine theta, which is this angle here. So now we have an equation for this here. Just a couple of things I want you to notice, and then we'll simplify this equation a little bit. Since we're squaring these, we're not concerned about the direction anymore, nor are we concerned about the direction of these. This is just a value, and an absolute value of the length of delta V. So V1 is the same as V2, and we'll just call that V. So we're just going to erase all the little 1s and 2s here because it's redundant. So now notice here we have, this is equal to 2 V squared minus 2 V squared cosine theta. So there's a, whoops, I put that in the wrong place. V squared, there we go. I need to hold the brush in my hand almost. So notice here we've got 2V squared here. So we're going to do that. Take that 2V squared times 1 minus cosine theta. And that's equal to delta V squared. Now we can take the square root of both sides, and we'll just have delta V is equal to the square root of 2 times V, I'm taking the square root of that, times the square root of this. How do I do this? Like this? Like that. There we go. Now I have an expression for delta V, and I'm going to get an expression for delta T, because the acceleration that you're going to feel, the acceleration here, is going to be equal to the change in the velocity and the time it took, divided by the time it took. So this is the change in velocity. What's the time it takes? Well, if you remember from before, we said velocity is equal to distance over time, and we want the time. So we're going to switch the velocity and the time. Do some cross multiplying here. So this is going to become T This is going to become v. We did this before with our other example. So here's the distance it's going to go is this distance over here. It's theta times r. So the distance is theta times r, and the velocity is just any of these velocities divided by v. So here's the time it goes, and here's the delta v. So if we want the acceleration, we're going to take all of this and divide by this. So I'm going to take this here, divide by this, theta r over v. Now this is going to be delta v over delta t. Delta v over delta t would be the acceleration. So we're getting very close to what we want here now. Notice we have a v we're going to have to invert this and multiply, which means this little v is going to come right to the top and become a v squared, like that. And we get rid of this one here. Now we have something like this. We have a root of 2 here, v squared over r, but we have an extra theta. So I'm going to erase some of this stuff here, rewrite this a little bit neater up here. So the acceleration here now is equal to v squared over r, and then root 2 over theta. This is some extra stuff here. And then the square root of 1 minus cos, whoops, let's make that a little neater. Square root of 1 minus cos theta. I'll erase this. So now we have this over here, 1 minus cos theta. We'd like to be able to get this cos theta sort of out of there because that doesn't really help us with what we're trying to do. Now, if you remember, what we're trying to do here is find the value of delta v, which was the top of this acceleration thing, as we make theta go to 0. So we're going to want to find a really small angle in there. For most functions, you can do an expansion for when your angle or your x value gets close to 0. In this case, obviously, if you get very close to 0, your value is going to be 1. At 0, it's going to be 1. But if you're very, very close to 0, the next term in that expansion is going to be x squared over 2. I shouldn't use x there. I should use theta squared over 2. This is in radians, of course. Very, very small. If you want to do the next term, it's going to be theta, this is actually 2 factorial, over 4 factorial. So it's going to be negative here, plus here, it's going to be minus theta to the 6 over 6 factorial. 4 factorial is 1 times 2 times 3 times 4. This is 1 times 2, so we don't actually need this. Now remember, we're going for a very small angle that's not actually 0. So we don't need more terms than just 1. So we'll just keep 1 term there, which means we're going to replace this thing here with this. Now if you put all of this in here, this in here, notice you're going to have a minus sign here, so it's going to be 1 minus 1. That's going to get rid of the 1. And then you're going to have a double negative. This minus and this minus, you're going to be left with theta squared over 2, a positive. So I'll just, all of this goes away, and you're going to be left here with theta squared over 2. Now, we don't need this. Let's multiply this all out. Well, this here we can take out. We're just going to have theta over root 2. That's the square root on this. Here we have root 2 over theta. And here we have v squared over r. This, of course, cancels with this with this. And we're left with v squared over r being the acceleration. And if you do this instantaneously, notice this arrow and this arrow would basically line up, and delta v would be straight in toward the center, hence giving you the geometry of it. And this would be the amount of the acceleration needing to go around, v squared over r. So I've just proved it to you using basic geometry and making theta go to very, very close to 0. And this would be your estimate for your v squared over r. Actually, it's an exact value for the centripetal or centripetal acceleration that you need to have in this direction to change the velocity from this direction to this direction in a continuous manner. So I hope that helped. I hope you found that interesting and useful, and I will see you in the next video. Bye-bye.